So if we look a little further into quantum mechanics, talk about the Pauli Exclusion principle. And this states that no two electrons in the same atom can have exactly the same energy. So it comes down to every electron in an atom has a different set of quantum numbers, has a unique energy content. Okay, so electron configurations. This shows the distribution of all of the electrons in an atom, and each component consists of a number denoting the energy level, and you may want to say main energy level. That's what this 4 is. A letter denoting the orbital type, that's the P, and then a superscript denoting the number of electrons in those orbitals, okay, or in that sublevel. Orbital diagrams, also known as orbital notation, okay, is the one with the arrows denoting each electron. Each box represents an orbital, half arrows representing the electrons with a relative spin or magnetic field going up, and one in the opposite direction, plus a half, minus a half. We have Hund's rule for degenerative orbitals, meaning orbitals at the same energy level. And when we're talking, that means really we're going to be talking about atoms other than hydrogen, so that this 2p sublevel, all of the orbitals are degenerate, meaning at the same energy level. The lowest energy is attained when the number of electrons with the same spin is maximized. So you can say that you fill in 1 electron per orbital before you start doubling up is Hund's rule. Okay, so oops, sorry, I thought it was much closer. Pauli exclusion, you're going to have 2 electrons in each with an opposite spin. Hund's rule, fill in each orbital before you start doubling up. And then we'll just add the Aufbau rule, which is lowest energy levels first. Okay, meaning electrons are going to be in the lowest energy level possible before they start moving to higher. Okay. What is the characteristic valence electron configuration of group 7? You should know this. They will be in S2, P5, and then whatever main energy level corresponding to the period that they are in. This family of elements will be the group 4, characterized by an S2, P4, meaning 4 valence electrons. Okay. Here's what I was talking about as far as determining electron configurations for any element. You can follow the patterns on the periodic table. The first 2 columns are known as the S block, and this is where your S sublevel is being filled up. Remember, helium is placed over here because it is an inert noble gas, but it is completing the 1s sublevel. This section of the periodic table is the P block, the D block, and then the F block. Remember that these really go right here in that 6th and 7th group. If you notice the period which goes across, this is the first period I'm filling in. The highest main energy level is the first. The second period, it's the second main energy level. Third is the third. Fourth. Notice the D block. is 1 less than the period that it's in, the F block is 2 less than the period that it's in. How do we use this pattern on the periodic table to develop an electron configuration? Well, say I'm looking for the electron configuration of this element right here. To get to this element, I have to fill in the lower energy levels first. So that means the first 2 electrons of this atom are going to fill in the 1s sublevel. And there's 2 electrons because it's got the 1s orbital in that sublevel. Then it's going to, okay, so that's this one. Then it's going to fill in the 2s sublevel with its s orbital. Then those electrons have to fill in the 2p. The p sublevel has 3 orbitals, so that means there's 6 electrons. Then the 3s next to electrons go there. 3p6. Oops. Oh, sorry, went the wrong way. 4s2. Remembering 3d, the d's are 1 less than the period they're in, so 3d 10, and then 4p, I'm 2 electrons into it, 4p 2. Okay. Okay. There are some exceptions to that pattern that you should learn. Okay, and it really occurs where there are enough electrons to half fill an s and a d orbital on any given row. For instance, copper, if we find copper, copper is here. From its location on the periodic table, we would initially think that this would be a 4s2, 3d, they actually mean chromium. So not this one, this one. 4s2, 3d, 4 is what we'd expect to have happen, but it actually is a 4s1, 3d5. If we look at the actual orbital notation, we have a 4s, 1, 2, 3, 4, 5. This would represent the 3d sublevel. If I draw in the actual electron configuration, you can see that this is a half-filled 4s, half-filled 3d, all of these electrons with the same magnetic spin number. Okay, this is a more stable electron configuration than if this would be double up and having an orbital open. Okay, so you should remember that that is a likely anomaly or an exception to the patterns. Okay, and remembering that that 4s and that 3d orbital very close in energy. Okay, those same types of anomalies will occur in the F block atoms as well. And we'll do some of these for homework or classwork.